We're delighted today to be able to welcome Dr. Monica Alexander, who is an assistant professor at the University of Toronto. So Monica is someone who's really at the forefront of quantitative demography. She took her PhD from the University of California, Berkeley. And since then, she's been working on a wide range of really exciting research topics. So including looking at the opioid crisis in America and looking at the differences by race in that respect, and aligned with some of the research that we do here in Southampton. She's really explored the use of Bayesian methods to estimate and quantify and forecast all sorts of different demographic properties, and she's also been leading on trying to explore the use of digital trace data for the estimation of demographic research. Today, she's going to be presenting a work on a Bayesian cohort component projection model to estimate adult populations at the subnational level. So I will hand over to Monica. We've got about something of around the order of 35 to 45 minutes, and then we'll take questions at the end, but do feel free to post some in the chat in preparation for when we get to that stage. So without further ado, then I'll hand over to Monica, but thanks very much for joining us today.
Thanks, Jason. Thanks for the lovely intro, and it's great to be here. There's such a great group at Southampton, and it's fabulous to be able to come and chat to you so easily, although one day it would be nice to also come in person. But the concept of traveling by aeroplane at the moment is sort of such a foreign concept. I don't think it's going to happen for a while. Let me just share my slides and then make them full screen. So hopefully everyone can see that okay. So thanks again. As Jason mentioned, I'm at the University of Toronto. I'm in the statistics and sociology departments, but I'm a demographer by training, mostly working on different issues of demographic estimation where we have not very much data or sort of interesting data as well. So today I'll be talking about a particular paper looking at trying to estimate subnational adult populations in data sparse contexts. This is joint work with Leontine Akema, who's an associate professor of biostatistics at UMass Amherst, and she's actually here today. So she'll obviously field any difficult questions at the end. Okay, so an overview of today's presentation. First, I just want to give a motivation about why we're looking into this estimation problem, and then talk about some of the data availability aspects, focusing on Kenya, which is the example that we sort of worked on, but just sort of talking about data availability more generally for low and middle income countries. And then the majority of this presentation will be talking about the model that we're using to estimate these subnational populations. And then illustrating some results. Again, these will be on Kenya, and just sort of summarizing and talking about future steps. Okay, so I think a lot of people in the audience, I recognize a lot of names. There's a lot of demographers here and population health researchers. I think a lot of us know in general in low and middle income countries, there's just not very good data on demographic and health indicators in general. And that's even going as far as we don't really even have a good idea of basic characteristics or the number of people by subnational area in some of these low and middle income countries. This is to do with a lot of different reasons. Most of the countries worldwide don't have good functioning vital registration systems, so getting ideas of births and deaths is quite difficult. Infrequent censuses and other sort of political and economic instabilities that cause data issues. But thinking about just purely like how many people live in particular subnational areas, this is a really important thing to know. If we think about, turning estimates of rates of risk of certain diseases or certain demographic outcomes, we often want to sort of turn those into numbers. So we need a denominator of the population at risk. And in particular, we're often interested in specific age and sex groups. So a big example here is the women of reproductive age. So women aged 15 to 49, who make up sort of the key population of risk of maternal mortality, for example, studying things like family planning indicators, fertility changes in fertility, that sort of thing. And more generally, we know that the risk of particular diseases and causes of mortality vary substantially by age. So obviously the big one at the moment is COVID. We know that the risk of dying from COVID-19 is much larger for those who are older. And so having a good idea of just sort of the population at risk is really important. So in terms of thinking about subnational population estimates do exist, and I think probably the main sort of source of estimates at the moment is through the World Pop Project, which is a really great and really important project run out of the University of Southampton. And so thinking about the World Pop Project and how those estimates are turned into estimates by age and sex, it's really taking the really granular estimates of total population and then using the last available data that we have in that country. So for example, from a census or a survey like the DHS, to disaggregate those total population numbers into counts by age and sex. And so this is a diagram that I took from Pizzulo that was published in Scientific Data, I think, but basically showing the flow chart of gathering the most recent data by age and sex, and then mapping that to the granular, these really granular gridded populations that World Pop has to produce age and sex counts. And so in this project, we're sort of coming at the sort of problem from a different perspective. And in particular, I think thinking from a demography perspective, we're usually thinking about populations, cohorts of populations moving through time and going through different demographic processes that either add people into the population or take them out. And so trying to think about how to model that process in data sparse contexts. So in particular, cohort component projection methods are sort of this big suite of methods in demography that are really informative when you're thinking about both projecting populations into future time periods and also back projection, so population reconstruction. So the idea is that we can think about specific cohorts of people moving through time and then tracking the change in the size of that population with reference to the main components of demographic change. So for adult populations, this is thinking about in and out migration from particular areas and also mortality at different ages. But these cohort component projection models in general are really quite data intensive when you sort of apply them in the traditional sense, because you need data on every single component. So you need data on population counts, you need data on, age-specific mortality and also age-specific migration flows. And so they're often just not really viable in these countries where we don't have very much data. And so in these contexts, when we're thinking about population projection and reconstruction, demographers often fall back onto simpler methods. So for example, linear interpolation, looking at change ratios and applying those at a more aggregated level. And so with that in mind, the goal of this particular project was to basically come up with a cohort component projection approach that would work in a data sparse context. So from a sort of outcome point of view, we're interested in estimating adult subnational population. So when I say subnational, I mean at the admin 2 level. So this is like the county level. So we're interested in getting estimates by age and sex using a cohort component projection approach that explicitly tracks people through time, taking into consideration changes in mortality and migration. And so we're interested in projecting into the future, producing estimates and also uncertainty around those projections. And as I said before, our starting point was Kenya, but we were really interested in trying to make an approach that was generalizable enough to apply to many different countries. And so this is joint work, as I said, with Leontine, and the paper that this presentation is based on is up as a preprint at the moment on arXiv, and there's the link there. Okay, so before we get into the model, I just wanted to talk about what sort of data do we have available in Kenya, and then also what sort of data do we have more generally. So for Kenya, there's 47 different counties that sort of subsetted within, I think, maybe 8 provinces, 8 or 9 provinces. And what data do we have? Well, through the wonderful IFMS international project, we have micro level data available for decennial censuses from 1979 to 2009. So we have 1, 2, 3, 4 censuses available that give us information on population counts and also some information on migration. I've put in square brackets here, 2019 used for validation, so I'll come back to that a bit later. We don't actually have the microdata for 2019 yet, but we have the aggregate counts that we use for validation. The other information, main source of information we're using here are national level estimates of both total population counts by age and sex, and also mortality estimates at the national level from the United Nations World Population Prospects. So World Population Prospects is an enormous population estimation exercise that's published every 2 years by UNPD. And they publish population estimates and projections for every single UN member country, as well as a whole bunch of estimates for different components like fertility, mortality, and migration. There are some other potential data sources that we could have thought about using, but at this stage we're not using for various reasons that I can talk about if people are interested. So we looked at DHS surveys and also census mortality. So just to sort of summarize, the 2 main sources we're using here are information from censuses and also national level information from WPP. And so in general, sort of the nice thing about WPP is we always have these estimates. We have these estimates for every single country, right? So national level population estimates are useful because we would like our subnational estimation, our subnational estimates to imply the same number of people at the national level. The other thing that we also always sort of have are these estimates of national level age-specific mortality rates through time. And we usually have some census data for the countries that we're interested in. So I think there's more than 100 countries on IFMS that have at least 2 censuses available. And so censuses are really great because they give us an observation of the thing that we're interested in. So population counts by age, sex, and admin 2 level. And they also usually give information on some sort of information on internal migration. So most censuses ask the question, you know, where do you live now and where did you live 1 year ago, or where did you live 5 years ago, for example? And we can use those questions to sort of get some information about where people are moving in the years before the census. There is a slight complication that I'll just mention here that sort of comes up in the modelling process, and that's the fact that these geographic boundaries, these admin 2 level county boundaries, may change over time, and that's quite common. It definitely happened in Kenya, and so thinking about what we're actually estimating when we say admin 2, those things have changed over time. The nice thing about IFMs is that they give give micro level data based on both the current sort of admin 2 definitions, but also do some standardization over time to make these sort of standardized geographic boundaries that are temporally stable. And we're calling these districts. So for Kenya, for example, there's about 35 districts compared to 47 counties. So these districts are great, but in practice, when you think about using these estimates, people are usually interested in getting estimates for the number of people by the most recent boundaries, right? So when we think about estimating, we need to produce estimates for the most current admin 2 boundary, even though we might not actually have historical data based on those boundaries. Okay, so now to get into the model, how are we actually doing this? So to start off with sort of introducing some notation. So the sort of overarching goal is to try and produce estimates of populations by 5-year age group. So in this particular example, we're looking at women of reproductive age in Kenya. So we'll be producing estimates for every 5-year age group between 15 and 49. And so just to introduce some notation, the thing that we're actually interested in is getting estimates of these sort of underlying latent true population counts for every age group A, time T, and county C. And so we're calling these things eta ATC. Right, so this is what we want to get estimates for. What do we observe? Well, one of the main things that we observe are population counts for each of the censuses. And so we're just defining these, the population counts that we observe as YI. So where I is just the ith observation in a particular census. And then where you see this notation with the square brackets, this is just basically mapping the ith observation onto the age, time, and county that we're interested in. So this particular observation relates to age group A, time T, and county C. And there's just a small note here to do with those changing boundaries issues. So sometimes we can't map our observations I onto the counties. We have to just map them onto a particular district level D. Okay, so where are we going with this? So as I said, what we're interested in is the underlying true, getting estimates of the underlying true eta ATCs, right? So we need some sort of model to describe how these things are changing over time. We need, and then those, the population counts over time, they change through changes in mortality and migration. So we need process models to try and describe the changes for each of those components. And then we also need data models which relate what we observe. In this case, it's going to be population counts and migration counts. We need models to basically relate the observations to the underlying processes. And then the final piece is this idea of having constraints. So in this particular context, as I mentioned before, it would be nice if the sum of our subnational populations implied a national population that was really close to WPP. So we want to constrain our model such that that actually happens. And then the other constraint that we consider is, by definition, the sum of internal migration must be pretty close to 0. Okay, so there are a lot of bits going on in this model, and it's kind of, you know, thinking about how to sort of explain it to a more general audience or even a specific audience is kind of hard. But so basically I'll try and give a brief overview of all the main bits in the model. So the first bit is just the central cohort component projection framework that sort of relates population counts to migration and mortality. And then talking about the model for mortality, the model for migration, the data models, and then the constraints. And this is sort of an overview summary of what the model looks like. And so the bit in red is sort of this main cohort component projection framework. And then we have these three sort of process models based on mortality, migration, and an additional age time multiplier. And then the top part sort of relates to the data model. So how does the data we see relate to this underlying process? So I'll try and quickly explain all these bits. Okay, so starting with the cohort component idea. So we know that at a sort of very simple level, we know that for adult populations, if we're thinking about, you know, for a particular age group at a particular time point, we know that the number of people in that group must be the number of people in the previous age group in the previous year, minus the number of people who died, plus the number of in-migrants, minus the number of out-migrants. So this is called the population accounting identity. It's sort of the bread and butter of demography, I guess. And we know that this must, in theory, be true for adult populations at least. There isn't any other way that we can create people or take them away. They can either be added in or taken away through migration or mortality. And so if we had data for each of these bits, we wouldn't have to do any statistical modeling. We could just like look at the right-hand side and add them up, and that gives us the left-hand side. Actually, in practice, and you know, this is sort of a lot of why statistical estimation in demography exists, even if we do have data on all of these components, they usually come from, you know, different data reporting systems. There's different types of measurement error involved. And so it's generally the case that the left-hand side and the right-hand side don't add up. And in this particular context, we have some information about population counts from the censuses, but we don't really know much about anything else. We have a little bit about migration. We don't really have any information about mortality at the subnational level. So the idea is that we need to model all these bits. So this is sort of, this is the equation that was in that red box in the diagram. This is our cohort component projection framework, basically just rewritten. So what's going on here, we're saying that population in a particular age group, time and county is that same population the year before, multiplied by the proportion of those people who survive, which is 1 minus the proportion who die, multiplied by like a net migration rate, and then multiplied by this additional age year county multiplier, which I'll come back to in a little bit, which basically allows a little bit more flexibility based on the data we have. Right, so this is essentially our sort of classical cohort component projection framework plus a little bit of error. And so we need models. We need to work out a model for gamma, which is our conditional probability of death, and phi, which is our which is our net migration rate. Okay, so just going through each of those components in turn. So starting with the mortality model. So as I said before, we need an estimate for the age-specific probability of death for every age group, year, and county. So this is a pretty big ask, particularly given we don't really have very much data on this at the subnational level. But what we do know is, in general, when we look at age-caused mortality, or all-cause mortality by age, there's a really, really strong age pattern in mortality. You know, basically all human populations have this really characteristic J shape over age, where infant mortality is relatively high and then it decreases, and then you get this sort of increase over age. And so given we know there's these really strong regularities, if we could find some reasonable age schedules of mortality that we could put in a model, that we could then sort of move up and down or twist based on data that we do have, that seems like a pretty good place to start. And actually, this is a really common approach in demography, sort of this idea of using model life tables to reduce the number of parameters that you can sort of change mortality with, but still get quite reasonable age patterns in mortality. And so what do we have in this context? We have national level age patterns of mortality from the WPP. We can use those estimates. And so what we do is we use those to basically tease out characteristic mortality shapes for a particular country. And then we model them in a, in a regression framework that allows us to sort of move those components up or down based on the particular county. And so in particular, we get these characteristic shapes of mortality using singular value decomposition, which is a very similar approach to the Lee-Carter mortality model. Sorry, I'm just gonna have a drink. And so for Kenya in particular, we have sort of three main components here. So the first component is just the mean mortality schedule on the Logit scale. And so this is for 15 to 49-year-olds. So it's just sort of increasing quite linearly over time, over age, sorry. And then the Y1 here is sort of is this component that captures just general mortality improvement over age. And then for Kenya in particular, like a lot of sub-Saharan African countries, there's this really big historical fact of the HIV/AIDS epidemic. And so the second component here that's going into the model is capturing differences in the HIV/AIDS mortality. And so these are those three sort of components that are going into our mortality model. And so again, the idea is that we're saying that on the Logit scale, our probabilities of death are some sort of linear combination of these components. And then we can estimate the relative sort of weighting of these components in sort of a regression framework. And so we have county-specific intercepts, which are just sort of modeled centered at 0. So we sort of expect them to be at the national level, I guess, but then there's some variation across counties. And then how are we modeling these beta coefficients? So instead of modeling them separately for every county and for every time point, we're essentially putting some sort of temporal correlation structure on these things. And so what this model was saying is the effect, the sort of level of those mortality improvement and HIV/AIDS mortality over time is something like what's happening at the national level plus some county-specific deviation. And then those county-specific deviations are modeled, sort of smoothed over time with a random walk. Okay. All right, so that was the mortality model. So just to sort of summarize, we're using this sort of like, I guess, an updated version of a model life table approach where we can take these really characteristic model mortality shapes over age and then change the level and sort of the slope based on what we see in particular counties. Okay, so the next piece is migration. So thinking back to that cohort component production framework, we have these phi's. So just like mortality, we need an estimate for the net migration rate for every single age group, every single time point, and every single county, which again is a pretty big ask. So unlike mortality, we do actually have some observations on these things. So as I mentioned before, from the censuses, we can derive in and out migration flows based on using that question about where people lived a year ago. But it's still a pretty big ask to sort of estimate a separate parameter for every age, time, and county based on this limited data. And so looking at the data that we do have, we notice that even though the magnitude of in and out migration varies quite substantially over time, when you look at the age distribution of migration, it's like amazingly constant. And so these little graphs on the bottom of the screen show basically the age distribution of in-migration for 6 different districts. So these are the IFM's standardized geographic boundaries. And the 3 colored lines are 3 different censuses. And so basically what these graphs are showing are the proportion of total in-migrants in each of the age groups. So, sorry, it's not very well labeled. But the takeaway is that there's 4 different lines. So over the 4 different censuses, these age distributions are really, really constant. So what we do is we sort of use that to inform our model and try and simplify the form of the migration model a little bit more. And so in particular, we're going to assume that the age pattern of migration is constant over time, but let the magnitude of migration vary over time. And so in particular, the process model for the net migration, the first bit is just saying what the definition of the net migration rate is. So net migration is in minus out migration divided by the population, the starting population. And then for each of the in-migration flows and out-migration flows, we're assuming that these things are basically the total in-migration flows for that particular year and county multiplied by a constant age structure that's unique to that county. And the same thing for the out-migration flows. So we have age-specific out-migration flows are the total out-migration flows multiplied by a constant age distribution. Okay. And so how do we model these? The sort of prior information, we just sort of assume we don't really have much prior information about the age distributions. And so we put flat priors on these things. And then for the total in and out migration flows, again, we sort of impose some level of smoothing over time. So we model these as a second order random walk. Okay. Okay, so the last piece of the model talked about mortality, I've talked about migration. The last piece of the model was this sort of plus error bit. So this age time multiplier epsilon ATC that allows for additional variation for a particular county by age and time. So why is this in the model? So thinking about our model for mortality and thinking about our model for migration, they were both fairly constrained in the sense that we were separating out the age effects and the time effects to be sort of independent. So we did this because we don't have very much data and it allows us to estimate these components. But by adding in this additional age time multiplier, we're allowing for additional variation for a particular county that's not captured by the mortality and migration. So it's basically where we have data showing variation away from these mortality and migration models, we can sort of account for it. And these things are modeled on the log scale with just a random walk that's constrained to have a mean equal to 0. Okay, 2 more bits. So the second last bit is, so what I've talked about before is talking about the underlying process model for the population counts that we're interested in. So these EDA ATCs. But we need also some way of relating what we see from the censuses to the underlying components. So, and we do this through a data model. So in this case, our data model is relatively straightforward. So all we're basically saying is on the log scale, the population counts that we observe are centered at the true population counts with some error, where the error is based on the fact that we're using a 10% sample from IPMS. Now there's 2 lines here, and this is just because of this changing boundaries issue. So this statement is everything's fine when we have data at the current admin 2 level boundaries. So this is for the most recent census where we have information. But for the historical censuses, as I mentioned before, we only have information at this standardized IPMS district level. And so basically what we say is the counts that we see from those censuses are you know, at the district level rather than the county level. Okay. And there's an additional data model for migration. So again, it's pretty similar. So again, the idea here is that we have these underlying parameters that estimate in migration flows and out migration flows, and we want to relate the data that we observe on those flows to the actual underlying model. And so again, what we're seeing here is we're just saying that the things that we, the data counts that we observe are centered at the true in and out migration counts plus some sampling error. And again, the sampling error is based on the fact that we're using a 10% sample. Okay, and the final bit is just these constraints. So I mentioned before that we want to constrain the estimates in our model such that the sum of all the counties over age for a particular year are pretty close to what WPP is saying. So in particular, we say that it's about plus or minus 10% of what WPP is. And then the other constraint we have in the model is essentially saying we expect the sum of all, for a particular county, for a particular age group in a particular year, the sum of all the in and out migration across all the counties should be about 0. Okay, right, so this is just to sort of summarize. So again, we have this, the central piece of this model is this cohort component projection framework. We have process models on mortality, migration, and then this age time multiplier. And then the top line represents the data models which relate what we see to the underlying processes. Okay, so just to sort of finish up with a few illustrative results. These graphs are showing estimated and projected populations by age for women of reproductive age in Kenya for 3 different counties. So we have Nairobi, Wajir and Baringo. And so in these, for this model, the most recent data we had were from 2009, so 2014 and 2019 were the projected estimates. So you can see that there's this huge variation in age structure across counties in Kenya. And in particular, Nairobi is just has a phenomenal amount of immigration such that the age structure doesn't decrease, population counts don't decrease monotonically over time. Looking at mortality estimates, so these are estimates of the conditional probabilities of death over age for all the different countries. So it turns out that estimated probability in Nairobi is relatively high. The estimated mortalities in Wajir were sort of lower than the national average. And then the estimates in Baringo sort of, when you look at the results of all the components, it ends up that these estimates are pretty close to the national average. And then looking at, so estimated age patterns in migration. So we have an estimate for both the age patterns in both in and out migration. So for Nairobi, I should have said before, but Nairobi is a county that has, you know, it's orders of magnitude larger than a lot of other counties in terms of population. And so this sort of population size is reflected in less uncertainty in the estimates in general. And so you can see that there's a pretty clear age pattern for both in and out migration in Nairobi, and some evidence that the out migration curve is slightly older. But for the other two counties, which were quite a bit smaller, there's sort of more overlap and more uncertainty in those estimated age patterns. And then finally, there's estimates for total flows. So this is like the total number of people moving in and out of these counties. So again, for Nairobi, notice that the y-axes here are on different scales. So the scale of in and out migration from Nairobi is like, you know, orders of magnitude higher than the other two. So it's pretty sort of estimated trend is pretty linear, increasing over time with net in migration. And then in the other two counties, there's sort of more uncertainty again around the estimates, but potentially some sort of estimated out migration in Baringo. Okay, and then finally, I mentioned, you know, hours ago, or at the start of this talk, that we didn't have microdata. So there was a census in Kenya in 2019. We don't have microdata for that census, but we do have, we were able to extract the aggregate counts by population counts by age and by sex and by county, based on what's published on the Kenyan Bureau of Statistics website. And so we use those aggregate counts to basically validate our model. So we compare the projections that we were getting based on these 2019 census counts, and then compared a bunch of different things, a bunch of different metrics to a baseline model, which was essentially just extrapolating the most recent trend out to 2019. And the result was that our Bayesian cohort component projection model performed a lot better, in some cases sort of an order of magnitude lower root mean squared error. Okay, so I made it. So just to summarize, so the goal of this project was to try and think about how we could model population reconstruction and projection in terms of the main sort of drivers of demographic change, so mortality and migration, in these really data sparse settings. And so it's kind of hard when you don't have much data, because cohort component projection models take a lot of, you need a lot of estimates for a lot of different parameters. And it's particularly hard at the subnational level because we can't really wave our hands and say that net migration is zero. We need to sort of think about in and out migration quite explicitly. And so what we sort of showed in this paper is that sort of using sort of classical ideas from demography in terms of model life tables and things of that nature, we can build a cohort component projection framework to get reasonable estimates and projections of populations, and also estimates of the drivers of population change. And so we sort of view this as a first step of sort of, you know, a conceptual idea of building these sorts of frameworks in data sparse contexts, we also view these estimates as complementary to what already exists out there. So that, for example, the World Pop estimates. And that's all I want to say. So thanks very much for listening.